welcome back everyone to the Hello World Guide. This is another episode of the Android game development series, and in this video we are going to implement a proper camera system. So in the earlier videos we had a rudimentary projection metric setup inside of our renderer. However, it's generally a good idea to separate that into a camera class, and then we can later on extend this class to have like 3D transformations as well. For now it's just 2D, but it will make it easier to add more stuff and keep it organized instead of pushing everything in renderer. So as you can see inside of the renderer, now we have made some changes, some refactoring. So first of all, we include the camera.h, what this camera does and how it functions. We'll just take a look at it in a second. And because the camera class is a pretty simple one, I have implemented it as a header only class because to allow the compiler to inline the functions, and also to it's generally easier than keeping two files because the functions are pretty small. So yeah. As you can see, we have got a new structure here called render data, and this contains a reference to a camera. We do not copy it by value, we just use a reference, and then a vector of draw commands as well as a vector of text commands. And instead of having a lot of parameters to this doFrame function, we are going to use this struct as a kind of way to pass these things like easily. So we have got a camera reference, draw commands, text commands. We pass just a const reference to our render data to this doFrame function. And if I open up render.cpp, you can see that in here we actually use that, but let's first take a look at camera.h. So in camera.h, our camera consists of a bunch of different values. It consists of a projection matrix, a view matrix, a position, and a zoom. So let's first understand, we have already talked about the projection matrix, of course, when we were programming the render, but the view matrix is basically another matrix. So when we are rendering any object, we use basically three matrices generally. First is the projection matrix, then the view matrix, and then the model matrix. So what each of these does is that we know that when we load up a mesh, or in our case we just have a single rectangle that we define as a vertex array here, a square actually, but for example in a 3D game we might have different meshes, and all of the vertices are specified relative to the origin of that mesh. We can call this local space. So the model matrix, the one that we have got here, as you can see, is the one that is responsible for converting our coordinates from the local coordinate system to the world coordinate system. And then this view matrix is the one that is responsible to convert from the world to the camera's view. So it basically is the inverse of the camera's transformation matrix, and it is essentially like a reverse. So for example, when we have got our object that is positioned somewhere in the world, instead of having it relative to the origin of the world, we are going to change its transformation so that it's relative to the position of the camera and also its rotation and everything. So in a 3D game, you might want to use a function like glm lookat for this. Currently we just use a simple position, as you can see here. We'll go over this in a second. And of course we have got the projection matrix, which converts the camera local or the view space coordinates into the clip space coordinates. The clip space is also the NDC, the normalized revised coordinate space, and that is basically the -1 to 1 space that OpenGL accepts, and we convert that, and that's pretty much it. And we have got a vector position, of course, for the camera, as well as a zoom value. So these two were new to allow us to actually control the camera. Instead of the render, we just had a fixed projection matrix. We have got this constructor here, and you can see that it takes a zoom value as well as a position value. So the zoom by default is 1 and the position by default is 0, just at the default like we had earlier. And then we initialize our zoom, position, and just leave projection and view at 0. Now instead of recalculating the projection or view matrix every time it is requested, we just store it once when the update projection or the update view functions are called. And since of course the camera does not need to know the width and height of the screen, we just take them as parameters in the update projection function, and then we get our projection just like we did earlier. Instead of using 1, of course we use zoom here. So zoom multiplied by inverse aspect and zoom on the x and y. So this allows us to basically increase our zoom value to make the view larger. And in our update view function, we just take the reverse the translation of the inverse of the position that we have got here. Technically it's supposed to be the inverse of this matrix, but since we have got just the position here, it's just equivalent to negating the position and then creating a translation matrix with that, and that is our view matrix. And then we have got some functions to retrieve the projection and view matrices. So in render.c we have changed our well, in our shader the only change we have done is that instead of calling it projection, we are calling the matrix projection view, because we are going to multiply the projection and view and then use it here. And the reason we multiply this first is because well, it just is generally, you know, going to be faster. Instead of having to compute it every time we need to calculate a vertex, we are going to just multiply the projection and view matrix before and pass that directly to the shader. So if I go to the update here, of course I've got the projection view location. Make sure that you change the string here as well. And if I go down to where we are actually doing our frame, you can see that now we first of all clear, after clearing, we update the projection with our width and height, and then we update the view matrix as well. Then we calculate the projection view matrix by multiplying the projection and the view matrices, and then we just you know, upload that matrix to OpenGL. And similarly we do everything just like we were doing before, and nothing else has changed. So inside of game.h, you can see now we have got a camera member variable here, and inside of game.cpp we initialize this with a zoom of 2.5 to you know, kind of just zoom out a bit. And one thing that I do here is that I set the camera position to the test position, and where we are moving I remove the check for test selected. This basically allows us to, you know, actually move our camera and see how it functions. So this will allow us to change the position of our camera and you know, see what is happening with that. So I'm going to go ahead and run the app right now, and you can see that we have got this here. As you can see, the high text is a lot smaller, even though it's still rendering with the same size, but now our camera is zoomed. And you can see that if I move my camera, you can see as I am taking my cursor down, the high is moving up because the camera is moving down, so the object seems to be moving in the other direction. Similarly, I can move it around, and you can see that it is working quite like we would expect it to be. And now our object is staying completely static, but instead we are moving the camera. So yeah guys, this is going to be pretty much it for this video. I'll see you in the next one, in which we are going to continue with the series. So make sure to stay tuned for that, and share this video with other people as well, and make sure to like and subscribe as well, and bye.